Good evening and welcome to week 9 of the live interactive session of Fundamentals of Micro and Nanofabrication. The course instructors are Professor Susoban Avasti and Professor Sankar Sarvaraja from ISC Bangalore, and I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. This is a brief about me. These are my details, the classroom link, the YouTube channel where all the recording of these classes are available, my contact details in case you need to contact me for any specific purpose. So till now, we have covered cleaning, we have covered additive processes, we have covered patterning. But what has not yet been covered is subtractive processes. That means one is we are adding something or we are depositing some layers. That's fine. Then we have patterned it, like we have marked the areas where we want the patterns of these depositions. Done. Then we have to remove the areas that we don't want. So this will be covered under the subtractive processes, or more commonly known as etching. That is removing layers or films of different thickness according to our need. Okay, so there are two different type of etching processes. They are like etching is etching in micro and nanofabrication is commonly categorized as two types: wet etching and dry etching. So in this week we will be covering wet etching. That is where we are dipping our wafer into some solution. That's why it is known as wet etching. So for any kind of etching, whether it is wet or dry, we have some figures of merit. That means the the key factors, or yeah, hello, are you saying something? Hello, Hari?
Yes,
Yeah,
sir, nothing.
okay, fine. So the some key figures of merit are: one is etching rate at which this removal of material occurs; etching rate uniformity, how uniformly it is etching; anisotropy, and selectivity. These will be covering one by one. Okay, these are important because whenever we are going to select what kind of etching process we will use, we will have to see on these figures of merit. Okay, so that we optimize our process and we select according to our need. So first thing is etching rate and uniformity. Etch rate or etching rate is defined as the change in thickness or the material removed, uh, delta D, by time. Say we had uh, we had a wafer on which we deposited silicon, on which we deposited, say, gold, and then we made some pattern of PR using lithography. Okay, and then we are removing this. So while removing, we'll remove this portion. We will cut out this portion in a sense and remove it. So suppose that this thickness was, the total thickness is, say, 200 nanometer, of which in 50 seconds I was able to remove, say, 150 nanometer. So this 150 nanometer that is removed, okay, that becomes delta D. That is the material removed, and time, that is 50 seconds, becomes the time T. Okay, so based on this, we can find what is the rate of etching of this process. Okay, so that we determine how much time we need. It should not be like, suppose it was removing 150 nanometer, but we had to remove 200 nanometers. So if someone is in hurry and takes out at say 50 seconds only, you will not be able to get the desired pattern. So to get the perfectly desired pattern, we need it to be optimized exactly when it's removing 200 nanometer. Or if you are keeping it for very long time, it might create some profiles which we don't want. So that optimization is required, and that is why etching rate is one of the important features. Second important parameter or figure of merit is non-uniformity. That is, it is not that all features on the wafer will get etched at the same rate, because there are some factors like smaller feature size may not etch at the same rate, they may etch slower. Why? Because there the diffusion might not be occurring, the material might not be reaching properly there because it's small, tiny size. Okay. Second is agitation and temperature. To make this etching process uniform, we have to continuously agitate the whole system. If it is not proper, then there can be some non-uniformity. Then temperature variations also play a role. As we know, rate of reaction is always dependent on temperature. Temperature plays an important role. So larger openings often etch faster, while smaller openings have issues with the gas bubble or mass transport. That's why the rate is affected. Then another important figure of merit is anisotropy. Or uh, to understand anisotropy, we need to understand isotropy. So isotropic etching means iso means equal or uniform, and tropic means structure. Okay, so isotropic, that means equal in all direction, both vertically and laterally. That will actually lead to, if we want, uh, say this is our deposited area, and we want ideally a structure which is deep like this. But if it is isotropic, what it will be, it will make a circular etching profile. Why? Because it is etching in all directions uniformly. So it might lead to larger opening than the intended. Then is anisotropic etching. That is etching occurring primarily in vertical direction. That is what we want, with minimal lateral etching. So then how to, we will be discussing a lot in details about how to achieve this anisotropy, because that is what we want. We don't want our structure to be circular or such patterns. We want it to be straight walled, vertically walled. Although perfect anisotropic etching is like an ideal situation, and it might not happen. Okay, so the key consideration is that in case of wet etching, they are typically isotropic. Whereas if we are going for dry etching, they are mostly anisotropic. But still, we will see why we still go for wet etching in some cases. Okay. So when we are talking about isotropic etching, okay, that means this is the mask that is covering the area that we don't want it to be removed. Okay. So if it is isotropic etching, it will have some undercuts, mostly like something like this, an undercut because if we have to reach to this thickness at the bottom of our H profile, there will be some undercut. Okay, so that means at the top we will get wider opening compared to the actual mask size. We will get a wider opening, and this area will be called as undercut, the top. So there is a factor that defines how much anisotropy is there. Okay. And that is AF equals to 1 minus lateral H rate divided by vertical H rate. Because this any material cannot be perfectly isotropic or perfectly anisotropic. So there will be difference in lateral H rate and vertical H rate. And we know how to calculate the H rate. Yes, anyone? How do we know the H rate in any direction, say vertical? So we have discussed that H rate is given by delta D upon T. So say in this case, this depth is 100 nanometer and this undercut is say 20 nanometer. Okay, so 20 this side. So say this structure was made in 1 minute. So in this case, the lateral H rate will be 20 upon 60 seconds, nanometer upon 60 seconds, whereas vertical H rate will be 100 nanometer upon 60 seconds. And then based on this, we can calculate how much is our anisotropy factor. If it is 0, that means both in both the direction the H rate is same. In that case, we say that it is a completely isotropic etching. Whereas if it is 0, that means actually there is no lateral etching. That almost this factors becomes 0. In that case, we say that it is perfectly anisotropic, and this is what we generally tend to achieve. Okay, because an undercut will increase the hole size or decrease the pillar size. Here it was fine, but if suppose we wanted to create a pillar like structure, we wanted to leave this pillar and remove all other things. So due to this undercut, actually the size that we the structure that we will get can be somewhat like this instead of a vertical pillar. So this is an important factor. How much is the anisotropy factor of the etching process we are going to follow? Then is selectivity in etching, because if you have a chemical that most removes something, it should not be that it removes everything. That means and one of the most important thing that should be saved or that should be protected is the mask. Here is not the physical mask of the photolithography process we were talking about. This is the mask or the protective layer that we had made. It may be of silicon dioxide, it may be of photoresist or any other material. Okay, so if this is a photoresist layer or say silicon dioxide layer or any layer, okay, and then below it we have gold. And okay, now we want this gold to be removed in this area, but this mask should remain there. So we will have to select an etchant that has a H rate of like higher H rate for gold compared to H rate for PR. So if we are saying what is the selectivity of this say specific etchant, say KOH, okay, this is potassium hydroxide we are using say to etch out gold. So then we will say what is its selectivity towards, say, gold with respect to photoresist. And then we will say that whatever H rate we are achieving for the film A means here it will be gold, and mask, that means the photoresist will be B. And if it is the opposite, sometimes questions comes in the opposite sense. Okay, because we might even be interested to know how much PR it is removing, because it must be removing some PR. And sometimes it happens that although it is slow, but the whole process takes so much time that our mask actually gets etched out. So we have to ensure what thickness we need to put our mask so that we are able to achieve the whole process without uh, any glitch. Okay, so high high selectivity is ideal, ideal case where the mask will not be affected at all, and the film that we want to remove will only be affected. Okay, and when we have a selectivity lower than 1, 1 is the highest selectivity. Okay, the mask may etch faster than the film. Okay, not highest, sorry. Yeah, 1 is the minimum required. It must be at least 1. And in case it is 1, even then we will see that etch rate of the mask and the film is same. In that case, still it will be a problem. It must be much higher. Etch rate of the film must be much higher compared to the mask. So ideally it should be infinite, or you say that very high. Okay, if this selectivity is infinite, we say it is good. If it is tending towards 0, then it means it is very low. And when we are getting selectivity lower than 1, that means the mask will actually be etching faster than the film, which is undesirable in any case. High, higher selectivity allows for deeper etch. As I said, that if we have a higher selectivity, we might need a thinner mask and it will work fine. But if we have a lower selectivity, in that case, we need to create thicker mask, because that will also etch faster. It is all about the chemistry involved, the concentration, how strong the etchant is, and the temperature. Sometimes the same thing can be selective at one temperature, but when it is the temperature is increased, it might etch out the mask also. So these are the considerations or figure of merit we have to take in account. Till here, any questions? Anyone, any questions? Okay. Are you able to hear me? I am audible.
Yes, sir. Yes.
Okay. So now how this retouching occurs. Okay. These figures of merit, this figure of merit will be relevant even for our dry etching process. These are common for etching process. So what is the process of wet etching? We start with a film with etching mask. Until here, we already know how to deposit a film, how to create a mask or a pattern of say PR or whatever we need. Photoresist or hard marks. So, sometimes physical mask like say tungsten mask with cutouts, that can also work if it is there. Or sometimes Teflon mask is also used. We will see TIMA process have that needs such mask. Okay. So what is the process that occurs? The fresh etchant reaches the film through stagnant layer. Okay. Then the chemical reaction occurs at the surface forming soluble byproducts. So if it is say SiO2 and some etchant HF, hydro hydrofluoric acid is a common etchant for SiO2. Okay, so it will form a compound that will be soluble in the solution itself, and the byproduct will diffuse into the bulk of the solution. That will not remain on the surface. It will just get soluble, make a soluble compound and get soluble into the solution. One key consideration is stagnant layer limits the process. The top stagnant layer, that is limiting the process. Second is the byproduct must be soluble for efficient etching. It should not be that it remains there or it is very tough to remove. Like what happens in case of, say, if you are dealing with aluminum etching, it generally happens that after some times, this byproduct is, one of the byproduct is aluminum oxide itself. So it is getting removed, but a layer of aluminum oxide actually remains there. So whatever time you etch, it will not etch out. Why? Because this have to be removed. And how? You have to take it out, wash it, and then start the process again. And then it is able to remove that. So such problems can occur. Okay, that's why one of the best way is that the byproduct is soluble, or you know what is the duration after which it will be made and how to make it soluble or how to make it go away. Then etchant selectivity is crucial to avoid mass degradation as well as substrate degradation. It should not be that say we have SiO2, we have a PR. It is selective for SiO2 compared to PR, but below it we have silicon and it etches out silicon. So will it be of any use? Anyone? See, it should be selective for both mask as well as the substrate. Although we are generally saying that it should be like it should be less selective for the mask and the uh, substrate, but uh, we are generally talking about mask, that it should avoid mass degradation, but equally it should not disturb or destroy or etch out our substrate. So since it is a surface reaction, there are two things like surface reaction as well as diffusion rate limited. These two part of the etching will be there. When we are talking about surface reaction rate limited, that part of etching will occur limited by the chemical reaction at the surface, whatever reaction it is taking place. It is very much dependent on the temperature since rate of reaction, uh, K, K is the rate of reaction, right? K is very much dependent on temperature, and it is very common that just changing 10 to 15 degree, we can double the rate of reaction. Second is diffusion rate limited. So how fast the fresh etchant, that is unreacted etchant, reaches the surface and byproduct is removed. This is important. This is one of the important factors when you have to do etching for a longer duration. It might occur that the whole solution gets saturated and the fresh part, that is unreacted part, is not able to reach to our surface fast. So there are some factors like stirring, agitating, and viscosity of the solution. That is an important thing that we have to consider. So when the reaction, that is, say you have dipped your wafer into a fresh etchant, so it will be directly surface rate surface reaction rate limited, because at that time everything is fresh, all the chemical is unreacted. That part will be affected by temperature and concentration. Then after some time, if the process is taking place, it will be then become diffusion rate limited, and this is affected by stirring and etchant viscosity. Less viscous, it will easily move inside the liquid, as well as if you are stirring and agitating continuously, you will be able to remove the byproducts, and the fresh etchant, the unreacted etchant, will try to move towards the surface. Then, yeah, till here, any questions? Okay, so the next thing, we have already seen that etchant can be isotropic or anisotropic, and if it is wet etching, it will often be isotropic, and if it is dry etching, it will often be anisotropic. So, what is the electrochemical nature of this etching process? So, uh, here in the process, positive and negative charges, charge domains, like some clusters of say positive charge and negative charge or ions, form randomly, and that they act as anodes and cathodes. So if it is so that if in this whole process there is some electrochemistry involved, that is the flow of charges involved, in that case, certainly the doping levels will play some role. Whatever is the doping level of the material to be etched, that will play a role, because of this electrochemical nature of this etching process, and that is why this etch, etch rate will also be affected by the doping level of our material. How much is the conductivity of the material that we are going to etch? That will again determine what is the rate of our etching. So, and as well as we have already seen that any kind of uh, impurity, say metal impurity, non-metal impurity, can actually contribute to some charge flow. That's why impurity in etchant can also, one is the dopant level of the material to be removed. Second is the impurity in etchant will also start playing a role, and that is why it will also impact our etching rate. That's why when we are taking the etchant, it must be pure and like clean from impurities, as well as since it is electrochemical and the flow of charges is affected by temperature. So temperature will again affect this aspect of the etching process also. That's why it is generally seen that highly doped areas where the uh, like conductivity is higher, say N plus area, P plus area, that will etch faster than undoped region due to the work function difference. These things occur. Then one of the we will be taking some examples of how etching is done. Though this is not a comprehensive example covering everything, but these are common etching how they are handled in our microfabrication. Okay, so one is, and you will be able to appreciate uh, why this wet etching is sometimes useful. One is, one and most common way is it is cost effective. You just have a solution, you have your wafer, you dip into it, shake it, like keep keep agitating it for some time, remove it, it is done. Although it might not be fully anisotropic, it has some isotropy, but still it is a faster process, cost effective, But at the same time, there are chances of contamination, there are chances of hazards because you are handling chemicals and sometimes very harsh chemicals like hydrofluoric acid, which is very dangerous to handle. Okay, so let's start with one etching example, that is HF etching of silicon dioxide. Okay. This is commonly used for isotropic etching of silicon dioxide, SiO2. This is the first thing we learned about how it is grown and how it is deposited. Okay, now we are learning how we are removing it. As I said, one of the common example is HF, and when HF reacts with SiO2, it forms a complex H2SiF6. This complex dissolves, and when it dissolves, the next layer of SiO2 is available for the continued etching. Now, if you buy any HF solution, you will see that it is generally we are getting something in the range of 40% to 49%. That is the commonly available HF solution. But this concentration is too reactive for microfabrication, and that, like, it will, if you directly dip it, it will remove everything, and too fast we will not be able to control our rate of etching. That is why it is diluted with deionized water to control. Generally, like, if we, you might encounter that we are generally making the concentration so to around 10%. 10% HF solution, we are decreasing the concentration by adding deionized water for control. We don't use city water or tap water to dilute it. It is diluted using deionized water. Okay. Dilution, this the dilution will affect our rate of etching. So, say if it is diluted so much that it is 1:100 ratio, 1 HF, 100 water. So, concentration we are decreasing from 49% to say 1%. This is used for cleaning oxides. Okay. But since it is a acidic solution and its pH will decrease over time, okay. So buffered HF, this is used to maintain constant H rate for better reproducibility, because this H rate will vary over time. You dip it at start, it will be vigorous, then it will slowly decrease. We don't want that. We want a constant H rate so that we can know that at what, in how much time it will etch out. It is always not possible to inspect with eyes, as well as like seeing it, you might be exposed to fumes and all. Okay, so we need to maintain that constant rate, and that is achieved using buffered HF. So, and this is generally known as buffered oxide etch. Any questions still here? You are able to uh, understand till here, Hari?
Yes, sir. So that
Okay,
what is the buffered HF, like what is the percentage of what, like ratio, sir, like what dilution in the, like,
that
in,
can be any dilution. We are just maintaining the pH. Buffer solution, you know, na, in buffer solution, what we do is that we maintain a constant pH. Whatever reaction takes place, the pH will remain constant. And pH means generally the, like, the consistent HF concentration will be there in a sense. You may be taking 10%. So if it is buffered oxide H, it will remain 10% throughout. But if it is normally diluted with DI, it might decrease to say 8%, or it might become 2% after some time, because reaction is taking place, and that this the complex um, forming with SiO2, that is also dissolving, and that might decrease the concentration. Fine.
okay, sir, okay.
But okay. So how to maintain this consistent concentration, that means it will not change over period of time, is by adding ammonium fluoride to create a buffer. That means the general, you see this formula. What is more prominent here? Hydrogen. Hydrogen plays an important role in this reaction. So hydrogen ion concentration is maintained by adding ammonium fluoride. This is used to etch silicon dioxide, and this is one like whenever you are going to any fab, they will not directly use dilute HF. They will mostly be using buffered oxide etching process to do the etching. Okay, so we can achieve uh, etching of silicon dioxide with a consistent etch rate. It will not vary over time. So it is like if with dilute HF with time, and if this is etch rate, it was fast and slowly decreasing. In this case, we are supposed to maintain a consistent rate throughout our time of etching. Fine. Some surfactants are also added to reduce surface tension and improve the penetration of the etchant into small features. Again, this is an advantageous feature. And one very good thing here is that SiO2 is grown from silicon. SiO2 is made from silicon and it contains silicon. But silicon acts here as the masking layer. So it is not going to affect silicon. When it reaches silicon, it will stop. It will etch out silicon oxide. And this is one advantage of buffered oxide etch. So what is the etching rate of HF solution? As we increase the HF concentration, higher the concentration, higher will be the etch rate. Lower concentration means diluted HF, like 1:100, 1:10. So if I was talking about 10%, right? So like in our lab, we are generally going for 10%. Or you are going for 1:1. That is 1:1 will be 50%, right? This gives, like, if we decrease the concentration, that is 1:100. 1 is HF and 100 is DI or the whole solution. Okay. In this case, we will get slower rate but highly predictable or highly controlled. We know at what speed it is etching. Okay. Compared to 1:10. So if I have to control the rate of reaction, fine. And as well as I have to know at what, like, it should slowly etch out this much uh, thickness, then I will go for, from 10% I will shift to 1%. If I need to remove each and everything and just in one go, then I can go for 1:1, that is 100%. Or if it is solution we are taking, in that case it will be 100% HF. In that case, it will, if you just dip it, it will go, everything gone. Okay. Second is higher temperature leads to faster etching rate. This one example I can that happened is that we made once we made a 5% HF solution and we were etching some features. Okay, so one of our labmate, he was like not able to wait so much. So what he did was he put the like he increased the temperature a bit. He just heated the solution a bit. Okay, say to 80 degree, I think. Yeah. And what happened is that within 4 5 seconds, the whole feature, actually whatever we wanted to keep, that also got etched out. So the temperature plays a very important role, and a small increase in temperature will also increase the rate of this etching very much. That is why generally this area where this wet benches are there, where we are working on this etchant, we are keeping that area at a constant temperature, say around 20 degree or 25 degree, and we optimize all our processes based on the temperature that we are maintaining in our system. So if the temperature outside changes, we must maintain the temperature inside so that we get the same rate, same amount of etching or rate of etching. Okay. Second, one example is silicon nitride etching. This is again a very important material that needs to be patterned. This is used for passivation very commonly. Okay, and cantilevers are also made using this. We will see what are MEMS cantilever. Okay, hanging structures of uh, they are very common in MEMS. So HF can etch out silicon nitride, but it is very slow, zero point 0.5 nanometer per minute for high quality films. Sorry. Till here, you are able to get everyone. You are able to understand.
Yes, sir.
Okay. Any questions? Any doubts? Please feel free to unmute yourself and ask questions in between. Not an issue. I am not taking a lecture. I am expecting you also to ask questions and clear your doubts. Fine. Any questions still here? Okay. So let's move forward. So boiling phosphoric acid H3PO4 is used for faster etch rate. So you see the etch rate has increased 20 times from zero point 0.5 nanometer per minute to 10 nanometer per minute. Zero point 0.5 nanometer is very less, like half nanometer. You will have just if you have deposited say 200 nanometers, to remove that structure you will need 400 minutes, which is around 6 hours, more than six, I think. Yeah, six 6.5 or 7 hours. Now, if you are going for 10 nanometer per minute, it will take 20 minutes only. So that is the difference. Silicon nitride requires a hard mask. So it generally requires silicon dioxide since photoresist does not hold up for long etch times. Because here also you see 20 minutes. Here you see it was how much? Around 7 hours, right? So photoresist cannot withhold for so much time. It will just get removed. That is why we require hard mask. Typically, silicon dioxide is used as the mask for such etching of the silicon nitride. And if we are using if we are using HF, then silicon nitride cannot be used since it etches silicon nitride. So by using HF, we can pattern the silicon nitride, the SiO2 over it, and then we can use it as the hard mask to create our pattern for silicon nitride. Okay, and then we can use boiling phosphoric acid to create our pattern over silicon, and it has select very high selectivity over silicon dioxide, about 5 is to 1. So if it is say 200 nanometer of silicon silicon nitride, just depositing 40 nanometer over it or say 40 is the optimal, right? So we can go for 50 nanometer of 50 nanometer SiO2. If we deposit over it, we will get our pattern. So after this, can anyone calculate if it is selective 5:1? So once we have removed this 200 nanometer of silicon nitride, how much of SiO2 will be left? Yes, anyone? After etching, say for whatever time we etched, say 20 minutes, okay? And the selectivity of boiling phosphoric acid is 5:1. 5 for silicon nitride, Si3N4, and 1 for SiO2. So if it is removing 5 nanometer of uh, silicon nitride, at the same time it will actually remove 1 nanometer of silicon oxide. So if we had made a mask of 50 nanometer SiO2 over, let me draw somewhere. So if we had this Si3N4 and this is 200 nanometer, and we created a mask using SiO2, okay, and the thickness we kept was 50 nanometer. So after the whole process is completed, that is this Si3N4 is etched out, this area is removed out, how much of SiO2 will be left? Yes, anyone? Yes. Anupam or Hari? Yes. And are you able to hear me? Like, am I audible?
Yes, yes, yes,
Yeah,
audible, sir. But here internet connection is poor. Whatever you said is something missed out.
yeah,
Can you repeat, sir, one time?
yeah. The thing is that uh, H rate, like H selectivity of S3PO4 phosphoric acid is 5:1 for silicon nitride compared to SiO2. Now, if we have a mask of thickness 50 nanometer of SiO2 over 200 nanometer silicon nitride, and we did the process to completely remove the area of silicon nitride using the SiO2 mask of 200 nanometer, we removed, and SiO2 was 50 nanometer. So after this whole process is complete, how much of silicon nitride will, how much of silicon oxide SiO2 will be left? So when it is removing 200 nanometer, it will remove 1/5 of it in the same time, which is how much? Yes,
40 nanometers.
yeah, 40 nanometer, right? So out of 50 nanometers, 40 nanometer is removed, etched out. So how much is
Remove,
left?
yes.
10 nanometer. So
Yes, yes.
when using the mask, we have to take care that the thickness of our mask should be enough to sustain this whole process. If someone has kept the mask thickness to be 30 nanometer, in that case, the mask could have etched out before our whole process was complete, and in that case, we might not be getting what we desire. We might be getting some, like the pattern will be removed after some time, and that's why we will not get our desired pattern. So we have to take care of these things also. Now we are saying that the etching rate will vary over time, but why? One factor is the atomic orientation. If it is a high quality film that is well arranged all the things are in proper connections, it is a well matched lattice crystal, it is a very good crystal. In that case, the film etch rate will be slower. Second is different methods will result into different etch rates. Different method of deposition. Say you are depositing the same thing using CVD. Anyway, that is actually dependent on the film quality itself. Or you are depositing the same thing using uh, this PVD like sputtering. Or you are depositing the same thing using, say, oxidation. You are growing it using oxidation. The quality of film will differ. That is the orientation, the uh, cracks, the uniformity, these things will differ, and that is why that will determine the H rate. So we must understand that if we are going to etch out a, like we have optimized the H rate for something deposited using say SiO2 depositing using uh, sputtering, the same H rate might not be available for one grown using thermal like oxidation, thermal oxidation, right? So we will have to optimize based on the type of deposition method also. Third is temperature. We have seen that the rate of reaction, rate of etching will be dependent on the ambient temperature, and that's why the ambient temperature have to be maintained. And then one thing is impurities. As we have seen, doping and impurities can significantly affect etch rates. Okay. Example: 1:1 buffered oxide etchant on uh, plasma enhanced CVD deposited silicon nitride at 450 degrees Celsius gives an H rate of 300 nanometer per minute. We are doing the reaction at 450 degree. Whereas the same thing, thermal oxide, that is thermally grown oxide, since it is of higher quality, since it is formed from the crystal of the silicon itself, so it will be more oriented and more uniform. That will etch much slower, about 90 to 100 nanometer per minute at the same condition in the same etching. So these are things that we have to understand, and we cannot say that if uh, it is just the same material, so what will be the difference? It's not like that. The quality of the material, quality of the film will also determine the etch rate. Now, what are the advantages and disadvantages associated with wet etching process? Advantage is it provides smooth wall profile since it is isotropic etching. The wall that we want, that will not be rough since it is etching out in all direction, chemically etching. We will get a smooth wall, and we can achieve deep etching with thin masking layer since chemicals are highly selective in nature. They don't react with any material. It is not that whatever comes in the way they will react with they are very selective. Third is simple setup. Very simple. You take in a beaker, you put the liquid etchant, you put your wafer, shake it, take it out, wash with DI. Very simple process, low cost and easy to handle. Although there are some precautions we have to take care. There are disadvantages like where we want high precision structures. For microfabrication, it was fine. For higher feature size, it was fine. But when we talk about nanofabrication, where the rate of etching is in nanometers per minute, and in that case, the profile, like small change in the profile in terms of nanometer, will actually affect our devices. In such cases, the sidewall control is poor. That means we cannot create very straight vertical sidewalls. That is one of the biggest disadvantage of wet etching. Second is temperature sensitivity. Any small change in the ambient temperature, it is not that it can be everything can be maintained at a fixed temperature. There are some factors that will actually change the temperature, humidity, a lot of things. Okay, and in such cases, small change in temperature can lead to large change in our H rate, and that's why we might not get the desired results, and that is one another disadvantage. One very important problem when we are shifting to smaller dimensions is poor sidewall control. Second is temperature sensitivity, and this will become more relevant when we are going for lower sizes because there we need better control. Third is contamination risk. Since you are dealing with chemicals and you are dipping something, you are taking it out, washing it out, and this using liquid and this, there can be some contaminants, particles, and residue can also accumulate on wafer. These are some disadvantages of our wet etching. Yeah, any questions still here? No. Okay. So when we are dealing with when we are doing this wet etching, we have to have some safety considerations. Since we are one of the common agent is hydrofluoric acid, HF, which is extremely dangerous. So you have to wear protective personal protective equipment, PPE, apron, goggles, face shield, thick nitrile gloves. Normal nitrile gloves will not work. We have to go for thick nitrile gloves, which are very thick, and everything, even your legs should not be exposed. Everything should be closed so that nothing, uh, like you are not getting exposed to HF. And HF has this property that there is no immediate symptom. You will not even, if by mistake HF gets on your hand, you will not understand anything. Like you will not feel anything. Nothing happens. You will just wash it out, done. But it can cause tissue damage and bone decalcification. It will get inside your uh, tissues, go to your bone, and it will decalcify it. So that whole bone will break. Okay. So one solution that has always to be kept, it's a calcium glu- gluconate gel, gel that has to be kept in ample amount in the lab where you are working with HF, and that is used to treat in case someone gets exposed to HF by mistake. Okay, then there is another kind of, we saw one common etching method that is using HF, and we saw, like, we understood what is this wet etching. Now let's come to some other kind of etching, that is HNAH. This is another kind of common etching method. H stands for hydrofluoric acid, again HF, which is used to etch silicon dioxide. N stands for nitric acid, which oxidizes silicon. And acetic acid, A stands for acetic acid, which is the solvent and diluent. Okay, so the basic reaction is silicon is oxidized to silicon dioxide by HNO3. So we have discussed SiO2 etching. Now we are discussing about silicon etching, making patterns on silicon. Okay, so silicon is first converted into silicon dioxide using HNO3 nitric acid, then we know that silicon oxide can be etched by HF, although HF does not remove silicon. Okay, and then acetic acid helps in facilitating the process, which we'll discuss later. Actually, it works as the solvent and diluent. So, what is the electrochemical? It is based on actually an electrochemical mechanism that random positive and negative domains form on the surface, acting as anode and cathode. And this is very similar to the corrosion current you might have learned in the intermediate chemistry, that how corrosion occurs, how electrochemical electron flow occurs inside the iron and Fe2O3 forms. Very similar to that, a high corrosion current and as high as 100 amperes per centimeter square. So a lot of reactions, electrochemical reactions will occur. And in these reactions, at anode, we will see silicon forming to silicon ion, giving out 4 electrons. And at cathode, NO2 that comes from HNO3 will accept the electron and form NO2 ion. Okay, so this will form, this will oxidize silicon in return, since silicon is now available as an ion instead of in the lattice. It will react with the oxygen present and it will form silicon oxide. So this is a corrosion reaction. That is, the material silicon is getting corroded or converted to oxide. And this, say, the first layer is etched, made into oxide, and then if it is dipped into HF, we already know that it will etch out the silicon oxide. NO2, this is crucial for this oxidation process, and this is formed from HNO3. And this whole set of reactions like HNO3 will dissociate and form NO2 and HO negative, and then like it is the byproduct of dissociation of HNO3, and then this NO2 reacts, uh, like helps in the formation of silicon oxide, and once silicon oxide is formed, it is dipped into HF and it will remove the silicon oxide. So HNO3 reacts by the intermediate reaction like this, HNO3 plus HNO2 plus HNO3, that will form NO2 plus water. Okay, this is a self-regenerating catalyst. That is HNO2, HNO3 will form an intermediate HNO2, like it will have different structures. So it will form HNO2 and HNO2 acts as the catalyst. It is continually regenerated, and as such, this is self-continuing process. We don't need to keep creating this, like keep adding some catalyst. Actually, HNO2 itself form, but there is a delay before this etching process starts, because this first reaction will occur and NO2 will form. Then only NO2 will facilitate the formation of SiO2. If we want to avoid this induction period, that is the delay, we can add ammonium nitride to provide intermediate NO2 by bypassing this induction period. Then why acetic acid is used? Because acetic acid have a low dielectric constant, that is 6.15 compared to water, which has a dielectric constant of 80. And as such, it will, if this whole thing is done, this solution is made in water, it will ionize faster. If we have a low dielectric constant material, the ionization of HNO3 will be less. And if ionization is less, the reaction leading to NO2 formation will occur easily, and that increases its ability to oxidize silicon. And that's why, and if more NO2 is forming, more oxidation is occurring, and we will be able to increase the etching rate. As well as it leads to improved wetting. Acetic acid wets hydrophobic silicon better. Silicon is hydrophobic. One of the common ways, if you are removing SiO2, to understand, in one class I said that when we are cleaning our wafer, there also we see that whole oxide is removed. And how we understand that whole oxide is removed, you dip into DI and take it out. If there is some water sticking over the surface, that means still some oxide is left. And once the whole oxide is removed, if you dip into DI, nothing will be there on the wafer. Everything, all the water will get repelled because silicon is highly hydrophobic. So, and we want to wet it. We want to get the reaction done. If we are going to use water, it will be repelled. Whereas uh, in acetic acid, it is uh, able to, like, acid is able to wet the surface much easier compared to water, since it is this silicon surface itself is hydrophobic. And that's why we get better etch performance and uniformity compared to using water. That is why acetic acid is used as the solvent in this process. To understand, so it is, this solution is combination of three things: HF, acetic acid, and HNO3. So the combination of these three, in what proportion it will be, okay, that is represented using iso H curves. Each point on the curve represents a unique composition of the unique ratio of HNO3, HF, and acetic acid. So based on this graph, iso H curve, we can get our desired rate. Like, we can choose our desired rate of etching. Okay. So example, like 50% HNO3, 20% acetic acid, and 30% HF results into 50 micrometer per minute of etch rate. And this is determined somewhere from these curves. So this is the composition of HNO3. So if you are taking this point, you will see that this this is 40% composition of HF. This is something like 42% of HNO3, and this corresponds to 57% of, okay, sorry, uh, acetic acid. This is acetic acid, and 57% of HNO3. So if we are going for the combination of these, we will get this contour. The same thing, same rate we can achieve when we are here, this combination. So it is combination of, yeah, it's combination of these three in different ratio will give different H rates. And based on this, there is a curve, that is iso H curve, that is used to determine the H rate. Since there are three things, we cannot plot it in normal rectangular coordinate. That's why such a curve is used. Yeah, so this is one example that when we are discussing acetic acid, why it is good. The same composition of HNO3 and HF with water will give a H rate of 38 micrometer per minute. But if we replace the same amount of water with acetic acid, we can get 50 micrometer per minute. So that's a reason that we go for acetic acid instead of water as the dilute uh, solvent or the base solution. We are not using water in this. So yeah, any questions still here? Now,
Sir, metals and also like some metal etchings and all like can you explain? Yeah.
yeah, that we will be covering.
Yeah.
That
Okay,
will be
okay, sir.
covering. Yeah, we have started with this
Oxides.
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 Yeah, we went into silicon nitride. Silicon etching is one big part. Okay, metal etchants like there is one list I have not actually put that you can find like mostly there are chemicals. Simple for metal etching, it is not that complex because metals are not like not crystals, right? So when we are dealing with silicon, it is very complex because we will see later that actually silicon, with the orientation of silicon also the etching will change a lot. But for metals, it is much simpler if we compare it with other thin films. It is simply that you have a solvent like etchant in which you dip it for a specific time, you take it out. Like in the process, you have to take care of these factors only, stirring and these things, and it will etch out. Like if you talk about this gold, KOH is used, KOH and iodine along with iodine. Okay, iodine, I think iodine was INR. I forgot the formula. Yeah. So iodine based KOH solution is used for this chromium orthophosphoric acid and combination is used. There are standard etchants available for metal etching, but for this we have to for silicon and SiO2 we have to do a lot of calculation to do the etching. Okay. So when we
This
are doing,
etching,
yeah, yeah, yeah.
so that etch rate, the etching, how much thickness and all using profilometer we can measure, sir, how much etch like it is up, how much depth of etch it is happening.
Yes, yes,
How
that is done using profilometer. In fact, in silicon also we can do that using that. In case of metals, na, you will be able to see with your naked eyes since there is proper change in color. And metal, we are not like we have to understand this that there are two kind of we are interested in two kind of etching. Okay, one is that say we are creating a profile in the material. This whole material is same as silicon. Okay, in this case we need to know how much depth this is because we need to say reach a specific depth. But if you have simply a layer like silicon over it, say chromium over it, gold, and we need to remove this gold and chromium. So we don't need to know the depth. We just need to know that yes, gold is not visible in this region. Is it clear?
yes, sir, yes.
Okay. So in case of silicon and SiO2, where we have to make patterns, especially MEMS kind of structures, there it is relevant and it is done using profilometer. But when it is like when we are dealing with simple metal layers, where we have to pattern for metallization and all, we don't need so much. Don't need to worry so much about how much thickness of etching has occurred. Yes, we need to know how much thickness is there. That is how we will determine what time we will keep it to etch out properly. Okay. So there are two limiting regions for our HNAH. Low HNO3 region, H rate is limited by the oxidation of silicon. So if HNO3 is very low, so the whole process will be determined by how slow. We already know that in a set of reactions, like if a process contains multiple set of reactions or chain of reactions, the complete rate is determined by the slowest reaction occurring. Okay, so in this case, if HNO3 is less, so the whole process is limited by the rate of oxidation of silicon, and so HNO3 is the controlling factor or the bottleneck. Whereas if we have put low HF, very small amount of HF, then oxidation might be occurring, but the removal will take time, and that is why it will be uh, limited by the ability of HF to H silicon oxide. So we have to choose based on the limiting factor. So we cannot control all the processes. So we have to wisely take in account what process we will control. Like HF, suppose we know it is the limiting factor. So the whole process will get dependent upon that. So we will put HF in lower amount, and we know that, okay, now we can control using that. So for higher H rate, because we want control, but we don't want it to be very slow. So for higher H rate, if the best way is to have a balanced amount of HF and HNO3, and that we can take from isotech curves. How this is done, we adjust the HNO3 and HF ratio to optimize the H rate based on the application. And since we don't want this induction period, the first delay before NO2 is formed, to be very high, low concentration of HNO3 is avoided. But there are some trade-offs, like higher HNO3 will oxidize the silicon faster, but may suffer from a longer induction period. Higher HF concentration will ensure faster silicon dioxide removal, but if it is too much in the system, HNO3 will be less, and then HNO3 will become the bottleneck. So we have to optimize based on the combination of these. Now, one problem that occurs with this HNAH is surface roughening. Okay, in HF rich regions. Okay, if we are going for high amount of HF, then the silicon surface remains oxide free. As soon as oxide forms, it is dissolved. It is made into the complex and then it is dissolved. But it will lead to roughness due to the HF's interaction with silicon. It cannot etch out silicon, but it creates roughness on the surface. And based on our uses, it can be advantageous or disadvantageous. If we are going for a good transistor, it is not good. If we are going for, say, a sensor and we want to deposit some functionation material on it, higher surface area is good. So it will all depend on our understanding. So you can go for a high HF concentration if you want a rough surface as a result of this etching, rough surface on silicon. Okay, yeah, wait, this is too much. Yeah. Then one important thing that is anisotropic etching of silicon. Here we were dealing with wet etching, so it was mostly isotropic. But for silicon, there is an interesting property, that is etching depends on the crystal orientation of the silicon. Crystal orientation means 111, 100 planes. We saw that our wafers can be 100, 111, and these things. So there is a property that 111 plane is the most dense plane or most atomically packed plane, and that's why it is much slower than the 100 or 110 plane. In silicon 100, if we are taking a 100 plane, means the top layer is 100. Okay, so on the top this is 100 plane. Okay, so the angle, like if you are etching it, you'll see that the etch profile will be something like this after etching, and this angle that is forming here or here, see, it will be 54.7 degree. This is a constant, and this profile is 111. And this property of selective etching of silicon planes is commonly used in MEMS. Since we know that the etching will stop at this profile, at this angle, the etching will stop. Especially, this is used to form structures like cantilever where they have to be hanging structure. So, suppose that we need to make a hanging structure. So, we will etch out the silicon below it. Now we have silicon and say this is Si3 and 4. So, this area becomes hanging and this angle is 54.7 degree, and we are able to get the cantilever structure. So, potassium hydroxide KOH is uh, capable of doing this anisotropically. It is cheap, non-toxic, and highly anisotropic because it will etch the 100 plane and it will stop at 111 plane. So we don't have to think about the etch rate itself. It will etch very fast, 400 to 600% fast in the 111 direction. So it will start etching in this direction and it will stop at this angle. But it has this problem that it is incompatible with the CMOS processing due to potassium contamination. Since we know that if we are dealing with CMOS technology, we don't want any metal ions, and potassium is a metal ion that can contaminate it. So this is not for CMOS processing, but for MEMS it is fine. Silicon nitride or silicon oxide is used as the masking layer because photoresist dissolves in KOH. For silicon nitride mask, it is having a selectivity of 10,000 is to 1. As, silicon 10,000 and Si3 and 4 1. So we don't have to worry about the mask at all. In this case, almost negligible change will be there. Second process is TEMA. This is again tetramethyl ammonium hydroxide. This is CMOS compatible. So it is an alternative to KOH, but it has lower anisotropy. It's not perfectly anisotropic, like not that difference in anisotropy, but it is still anisotropic and it works fine because somewhere you cannot use KOH. It is fine if you are using TIM. Okay, it provides 1 micrometer per minute etch rate for 100 plane. Since it is OH negative ion based, no potassium is potassium or other alkaline contamination is not there, but it still requires hard mask. So here also the mask, the pattern mask we use is hard mask like silicon nitride or silicon oxide. Here also the etching will stop on 111 plane. So what are the affecting factors in this anisotropic etching using wet etch? Anisotropy is easily possible in dry etching, but for wet etching, to achieve anisotropy, special cases are there. When you have to etch for a longer time, it leads to self-limiting etch as 111 plane slows down etching. So at 111 plane, the etching will stop very slow. But one problem is that if it has small opening, it leads to trapezoid shapes. Like if you have such opening and it is in 111 plane, actually the etching will be something like the etch structure will be on the top. We will get a structure like this. So if seen from the bottom, it will, like from the side wise, it will be a trapezoid shape. While if you have a big rectangular shape, a big opening, it will give you a rectangular shape. Even if you have a opening of circular opening, after doing this etching for a longer time, you will get a square shape since it is stopped by the 111 plane, and that will lead to square shape, uh, square rectangular shape on the top. So if we are starting with a 111 silicon, it will give a slope profile of 54.7 degrees. Whereas if we want a vertical profile, a bit better, the profile verticality should be a bit better than this. We can start with 110 silicon. So for silicon 111 uh, for silicon 110, it, it has a different geometry than 100, and that's why it is uh, it is able to provide vertical sidewalls useful for microfluidic application where we want to make some channels. Okay, tubular structure, not like channels in our silicon for some flow of microfluid. In this case, what we can start with 110 silicon and we can get uh, vertical walls, almost vertical walls. Then sometimes we might need to go for through hole etching, that we want a hole to be created. There is a silicon wafer and we want that it, ideally we want that it is etched out in this region and we create a hole. Okay, it can be useful for MEMS and microfluidics. So the depth will be dependent on the opening of this mask as well as the slanted, like if the mask is open for this much, so there is slanting. We already know there is an angle, so it should be able to reach till the end of the wafer. Then only we can achieve the thorough hole etching. In this case, it requires precise control of mask design and etch time to avoid over etching. Otherwise, the it might be that we just want it to go till there, but not completely. We want to make a membrane, thin membrane, and we want this membrane to be say 20, not 20 will be very less, say 2 micron, 2 micrometer. In that case, we will have to do a perfect control. And in this case, you see that this measuring it again and again by profilometer will be helpful throughout our process. This second. Then second thing is we have talked about nowadays gallium arsenide is one of the common uh, compound semiconductor being utilized, but it is not we are not able to uh, do gallium arsenide etching like the silicon because it has some complex chemistry, and that's why make, making the etching process anisotropic is a bit difficult. It has two phases. Since there are two materials, it has two phases. That is 111A, that is gallium phase. This is less reactive and produces rough surfaces. Whereas for the arsenic phase, that is 111B, it is more reactive. And in this case, it is diffusion limited etching, results in shiny surface. So, and these factors will actually impact the optical devices that are made using gallium arsenide. So the method to etch gallium arsenide is Carro's etch method. It contains sulfuric acid, which oxidizes gallium arsenide. So if we are comparing it with HNaH, it is similar to that, but here instead of HNO3, H2SO4, sulfuric acid plays the role of oxidizing the gallium arsenide. Then hydrogen peroxide provides oxygen for oxidation. So it is combination of sulfuric acid and hydrogen peroxide that does the uh, etching. So there HF was there and HNO3 was there. So HNO3 is replaced with H2SO4, sulfuric acid. HF is replaced with hydrogen peroxide. And here water is a good diluent. Okay, so water is used, and that is Carro's etch method. The isotech curve will be very similar to the HNaH still here, just the chemicals will change. So instead of HF, it will become H2O2, here it will become H2O, and here it will become H2O2. It is similar to HNaH, where the combination of H2SO4, H2O2, and water will determine the etch rate variation. But the problem is that etch rate differs for 111A, 111B, and 110 orientation. This is and the etch rate is anisotropic, and that is why it leads to different surface profile for various crystallographic orientation. For the arsenic phase, that is 111B, there is higher etch rate and it gives us smoother surface. Whereas if we are seeing the 111A, that is the gallium phase, that have lower etch rate and rougher surface. So in this case, the hard mask that is used, that will actually have some effect on orientation. The orientation of masks relative to the crystal affects the etch profile. If we have a square mask, that is square in shape, it produces sloped or vertical side walls depending on orientation. So unlike silicon, where there was it was just silicon, so it was limited by the 111 plane of silicon. But here there are two materials; they have their own orientation. So both of them plays role. Whereas if this will determine like it will give sloped or vertical walls. Whereas a mask with just 45%, 45 degree orientation will lead to perfectly vertical sidewalls. So it is combination of HNAH and TIMA or KOH. So it has the uh, properties of carriage H is like combination of not combination analogous to HNAH as well as KOH. KOH or TIMA H, they are same, just different materials. Now in the etching process, there is one thing that is commonly used is etch stops. Because we don't want the etching to be continuous. We want etching, but we might need to stop it at a specific point. And it might be that it is not always time dependent. We want that in one orientation the etching stops, but it continues in some other orientation. So how do we do that? A layer that stops etching at certain point is used that prevents overetching. So say after, suppose that we want that etching continues in vertical direction for say 20 nanometer, but in this direction has to widen a lot. This hole has to widen. So we will put some material here during the uh, deposition of the thin film itself, some film that will stop the etching. And this is useful for process stability and precision in thin film fabrication, where we have to control the film, but we have to widen out. And highly doped boron or boron doped silicon that acts as an etch stop for KOH and TIMA. So we know that 54.7-degree angle has to be made. So if we want that at say 20 nanometer, not 20, say 1 micron, it has to stop, and then we have to broaden our shape or the structure we are making. So uh, we already know that using ion implantation, we can do doping, and we can do doping at certain depth also. So we can have a highly doped boron, a large amount of boron doped at the depth of 2 micrometer where we want to stop. So automatically at that point, the TIMA or the KOH etching will stop. And that is due to the electrochemical nature, since we know that the conductivity also plays a role in the etching process. Why these are used? They allow for consistent etching without precise timing. So here we don't have to worry about time. We don't have to take it out at specific time and thing. Okay. And we are able to make uniform thin membranes. Since the etching will be at same level, okay, like we want etching to be say 2 micrometer thin membrane, okay, so there can be a risk of over etching, and we might get somewhere 1 micron, somewhere 1.5, somewhere 2. We don't want that, so we already made a profile of 2 micrometer, and then we are risk free of over etching. Etching stops automatically at the boron doped layer, a thin layer of boron doping, and we can stop the whole etching at this thickness itself. So one one common use of this is in MEMS cantilever, making MEMS cantilever. MEMS is micro electromechanical system. That is where we have 3D systems, or you say physical systems in a micro scale. So there can be hanging cantilevers, there can be gears, not exactly pulley, but pulley kind of structures, gears, system of micro channels, all these physical 3D structures in the silicon on the silicon wafer in the micro level, okay, which is very commonly used for sensing and actuation uses. Okay, so one common use is making silicon nitride cantilever that can vibrate. and we can find out the resonance and all. Okay, like I showed this silicon nitride thin layer, and then below it is silicon etched. So, and this side it is all solid. So, and then again below it we can have silicon. So this structure will be a cantilever. It is commonly used in sensors, actuators, and resonators also. So how it is made? We start with a silicon wafer, deposit silicon nitride over it. Let me use a different color. So we deposit silicon nitride over it. Use LPCVD to deposit silicon nitride on front as well as back of the wafer. So both sides we are depositing. Then we do photolithography using a photomask design and define the cantilever shape, whatever shape we want. So we pattern it, say, then we do the dry etching. That is, we remove the exposed silicon nitride. That is, uh, like I showed by removing, right? So this is silicon. Then now we have just silicon nitride layers, and that also patterned using whatever pattern we want to make wherever we want to make the cantilever and this thing. So we perform plasma dry etch. We will discuss about dry etching in the next week. Okay. Then next part is relevant for what we are doing now is that use KOH or TMA to selectively etch silicon beneath the silicon nitride. So it will be dipped inside, and we know that silicon nitride acts as a mask for silicon in TMA etch. So what will happen is that it will start etch out and create a structure like this till some depth here, and here also till some depth on both the sides. And if you don't want anything to be made on the back side, you just keep the silicon nitride intact, don't pattern it. Fine, not an issue. Okay. And this will result into our overhanging silicon nitride, and this will be the cantilever, and that can be used for further uses. So it is capable of vibrating. So if you see from the top of it, you will just see uh, like a rectangular silicon on top view, and this there is a hole here, silicon hole, and from the top side, you will just see a rectangular silicon nitride strip. If you see the side of it, you will see a hanging one. So this one will be Si3 and 4, and there can be some structure here, and this will be silicon. So this is the side view, and this is the top view. side or the cross-sectional view. Now, there is one thing that is defect etching, and it is used to delineate and magnify defects in semiconductor materials. This is particularly used to detecting dislocation, precipitates, and junctions like PN junctions and all. Because in this whole process, there is a problem that the defects are often too small to detect optically, and that's why defect etching is used to enhance the visibility of defect. We want to know where the defects are. We can go for defect etching. Since the defect sites have altered etching rate due to lattice stress, we know that when we have proper plane 111, 100, we know their property. When we have some defects, they will result into pits or hillocks. That means the profile was supposed to be like this, but actually it will become like this if there was a defect, there is a defect here, or it can become like this if there is a defect here. So such things are used to enlarge the optical visibility, and then you will be able to check that this area has defects using optical microscope, since you can now see the pits or hillocks, and that's why you are able to easily scan the large area to understand, okay, this area have defects. So what are the common etch is? One is dash etch, that is a modified form of HNA etch. Take 8 hours to develop, and this reveals defects as pits. So there are some other etch like Stelt, Seco, Skimmel etches. They are faster and more selective than dash etch, used for 111 and 100 phases to detect the defects. There are some special uh, defect etches like right etch that combine HNO3 and chromic oxide. So combination of this, and this has a longer shelf life and used for PN junction finding. Like if we need to find where the PN junction is, it cannot be optically found out. Okay, so in that case, we can go for right edge. Hello, am I audible?
Yes, sir. Yes.
Okay. There is another etch method, that is bromine based etch, that is useful for distinguishing A and B phase of the gallium arsenide. A is for gallium, B is for arsenide. Then there is silver etch that is applied in epitaxial thin growth for defect identification. We saw that in epitaxy, defect like they are to be defect free and all. So to identify this, silver etch is used to confirm that there is no defect, or if there is defect, then discard it and these things. Then comes metal etching, which you were asking. Okay, so aluminum etching is done using simple uh, phosphoric acid, HNO3, and HF combination, or separately also. Like this is a combo. This is actually standard. It is available uh, like it is standard. Like if you buy a aluminum etchant, you will find this standard phosphoric acid, HNO3, and HF combination. Then and this gives a H rate of 150 to 100 nanometer per minute. And this has the that, like I was discussing, this is the problem that after some time the etching rate will become a bit slow. So we have to take it out, put in DI, and then again etch it. Then gold etching, it we already know that to etch gold, we can go for aquaresia. But if we want to deal with photoresist, aquaresia will remove photoresist. So iodine-based etchant, iodine and KOH combination is used for photoresist compatible gold etch. And in case of metal etch, there are not so many complex things. It is just etch rate that will depend on temperature and the chemical. But there is a challenge if we try to etch some materials like platinum, which can be etched using aquaresia, but it is incompatible with photoresist. So how to do it? It is done using lift-off technique, and this is one very common technique that is used to deal with metals which cannot be etched conventionally. How it is done? It is simply that instead of patterning the thing that we want, we pattern the thing opposite to it. Like, I will just explain it like this. Suppose that we have this wafer. We want to create some patterns of, say, patterns of platinum or palladium. Okay. So what we will do is that we will put, uh, let's put, we will put photoresist. You are able to see this. Just doing spin coating and all. You are able to see it. Hello.
Sir, yes, sir.
Okay. So then using, oh, sorry, using our standard lithography process, what we'll do, we will create an inverse profile of whatever we want to create. Suppose that we want PD in this area, so we will remove the photoresist in this area. So we will create an inverse pattern like this. Wherever we want it, we will remove that. Then we will deposit the PD over it, and when it's deposited, it will be deposited like this, layer of it, and then we'll put into stripper. We talked about stripper, and what the stripper will do, it will remove this PR, left out PR, and when it is removed, it will remove the PT deposited over it. And this technique is known as, like, this will remove, and we will be left with the our desired pattern over the wafer. And this technique is called as lift off technique. But in this case, one problem occurs, and that is that if the PR was like this, then the deposition will be continuously over it, and it can lead to, like, it might not get removed. So to do this, we have to take care that the profile should be something like, ideally it should be something like this, so that when the deposition occurs, the material deposits here, here, and here. Instead of continuity, there will be a breakage. So this one will be the PR, okay, and this one will be, say, PT. So we have to take care of this, and this is generally done using lift off resist, like a layer of lift off resist, and then over it PR is put. That makes the profile inward or a negative profile. Okay. So in lift off, there are the challenges like effects, photoresist profile effects. So we need a T profile preferred. That is, we have something like this profile of PR, and this is done by generally using lift of resist below it and then PR over it. Okay. The best practice is prefer evaporation over sputtering to avoid sidewall coverage, and photoresist profile. This side profile is to be controlled to improve our results, and that can be generally done using lift of resist. That results in uh, T-shaped profile that it will like etch out a bit more. Like while developing, it will develop a bit more than the PR, and that's why it will create a T kind of structure. And this reduces sidewall deposition, making liftoff much cleaner, and there will be no sidewalls, like no stray marks will be there. Yeah, and this we have covered. Okay. Based on this, we have some questions. Okay. This we have mostly discussed. Okay. Anyway, I have given the answers also. Okay. These are all solved. Any problem in this, you can discuss and you can even ask in the class, not an issue. Okay. So, any doubts still here?
Nothing, sir, nothing.
Okay. So, you are
Let us.
understanding what is being covered. Yeah. So, the next topic is dry etching that we'll cover in the next class. So, that's all for today. See you all in the next class. Thank you.
Thank you, sir.